This is the 8th video of the series Business Forecasting, and we were discussing time series analysis. In today's video, we are going to discuss how to implement simple linear regression. I have divided the video into two videos because in the first part I want to discuss the theoretical part of simple linear regression, and then in the second video we will discuss the implementation method and also the interpretation, because otherwise the video will be too large, which I don't want to happen. Okay, so first of all, let us recall this time series versus cross-sectional data. We have already discussed this in our second video in this lecture series, but let us recall it. A time series data is when your data is arranged in this way, like in the order of the time. Here the time is day, and you are measuring the temperature at 10 AM in each day. So this is a series of data taken throughout the time, and hence it is called the time series data. And then this is the cross sectional data. What is the cross sectional data? Because you are taking one time point, let us say day number 10, and in that day you are monitoring the number of persons versus the temperature. So you are trying to see whether there is any relationship between number of person and the temperature. So this type of data is called a cross-sectional data because it is taken in a particular point in time. Now, primarily the method of regression is related to cross-sectional data, where we are trying to do causal analysis. So primarily the method of regression, simple linear regression, is related to causality. Why causality? Because we are trying to see whether the number of persons, we call it X, whether that is affecting our temperature, which is Y. So in this case, our X is number of person and Y is our temperature, and we are trying to see whether temperature is related to number of persons. So if we increase the number of person, whether the temperature also increases, and so on. So therefore it is related to the causality of Y with respect to X. But we can invoke this idea of causality into time series analysis as well. How? Because see, in a linear relationship like here, Y is explained by X, but what will happen if you replace X by T, that is the time. If you just replace X by T, so these equations become Y is equal to beta 0 plus beta 1 into T, and therefore as if we are saying that in the time series the data, temperature data, is dependent on day. That means the explanatory variable or the predictor is time, and the response variable is temperature. So in this way the idea is invoked in the time series analysis, and in case of time series analysis the time variable is taken as the independent variable or the predictor. Now you know that we are not dealing with any population data. Ultimately whatever data we have, no matter what, is a sample data. But still, in order to understand the calculations and the procedure of sample data in case of linear regression, let us first start with the population. So we are trying to plot the household income versus food expense. So our idea here is that our Y variable, that this is the dependent variable, and this is your X variable, that is the independent variable. So by the way, this terminology should be clear to you. The variable that we are trying to explain is the dependent variable. This is called the dependent variable. This is also called the response variable. This is the dependent variable or response variable. Similarly, this X is called the independent variable. This is the independent variable, also known as the predictors. So in this way, the food expenditure is the dependent variable, and the household income is the independent variable. Now there is a line that is shown here which is having this particular relationship, that is mu y is equal to beta 0 plus beta 1 into x, where beta 0 is the intercept. This is known as the intercept and this is the slope. So if you want to plot it here, then this is the intercept value, that is this is your beta 0, and what is beta 1? This is beta 1. This is your beta 1, given that this is 1, that is x is equal to 1. When x is equal to 1, then the change in the value of y variable is the slope of the line, that is beta 1. Anyway, but let us understand this graph very well. First of all, the line goes through these points. These are the mean value of these distributions. So check here carefully. The center point of these distributions are the mean values, and the straight line goes through that mean values. Therefore, this point is your mu y for x is equal to 2000. This point is your mu y for your x is equal to 1000, and therefore this line is a straight line predicting the mu y value. So therefore your actual y value can be anywhere in the line depending on the distribution, but this straight line, this equation is trying to find the mean value only. This line goes through the mean value of these distributions. So if you can reflect on this once more, we have many values of x, every kind of possible values of x, and then for each x we are having one distribution for the values of y, but this straight line is trying to predict the value of mean of those distributions. So the mean of those distributions will lie on this given straight line. This is the population regression line. Now, as we have mentioned earlier also, we don't have the population for study. So although we have this equation derived, we cannot take any direct benefit of this equation as of now. So what we will have at our exposure is a sample data, and let us see this sample data very clearly. First of all, you don't have all the x values with you. You will be given x, y pairs of values. So therefore, discrete values of x are at your exposure. For example, 105 is there, 110 is there, 120 is there, 125 also there. Some other values are also there. In this way, some x values are given to you. That means not all the x values are known to you. Moreover, for a single x value, you will have only one y value. So therefore, if you just recall the previous distribution, so for example, for this particular x value, you have one distribution with a certain mu y value at the center, but now you only have one y value, maybe some this value, just one value is given to you in the sample, and similarly for all the x values. By all the x value, I don't mean that all the x values are available to you, only the sample x values, those are available to you. So as per the graphical representation, these are the sample x values and the sample y values. So once this is given to you, our idea is to find a best fit straight line using this x and y pairs, and from the best fit straight line we will find the equation of the straight line, and these parameters, that means these sample slope and this sample intercept and this sample slope will be an estimate of beta 0 and beta 1. That means population intercept and population slope. So in this way we have to proceed in case of sample information. But then the next question that arises is how to find this B0 and B1 value. So as we have seen or discussed here, that your B0 is an estimate of beta 0, which is the population parameter, and B1 is an estimate of beta 1. This is also a population parameter and this is derived from the sample. But the question here is how to find this B0 and B1. Normally we will take the method of mathematics and calculus and find the errors. First of all, we will need to find the errors. What are the errors? Error means for a particular set of x1 and y1, we can calculate the expected value of y if we know the B0 and B1, and if you subtract that from y1, this is the actual value. This y1 is the actual value and this is your predicted value. So if you subtract the predicted from the actual, that will give you the error. This is the error. And you can write that. That means you replace the EY in terms of this. So this becomes your error. And now, since these errors are placed in both the directions of this line, that means both positive and negative errors are possible. So we will square these errors and minimize. As you can see here, these error terms will be minimized. The square of error, that is the sum of squares, will be minimized. And what is the method of minimization? Like EI is yi minus EY, that is yi minus B0 plus B1 into xi. And then if you do the square, this is the squaring, and then use the partial derivative method. Take the partial derivative and equate that to 0. And you don't have to solve this now because this is not the part of our analysis. We know that this can be solved, and if you solve that, then you get the values of beta 0 and B0 and B1. As you can see here, these values will be obtained like this. And you don't have to solve that. For solution method, we already have our softwares, so we can either use Excel or maybe other softwares like SPSS or Minitab or even R or Python, anything. So you don't have to calculate these values manually. Of course you can do it if you want, but you don't have to do that. Main idea is to get these values, that is the values of the sample slope and sample intercept, and then interpret the result of the regression in a detailed manner. So that is our primary target. So use the comment section also to inform me whether in the next video I should use Excel or these advanced tools. My idea is to use these tools because Excel will not give you the full result. Of course, you can generate full result by using some manual calculations and manual graphing also. But in case of these tools, the tools will generate not only the regression result but also some plots and other analysis which can be helpful for interpreting the results. So before closing this video, let us discuss the assumptions that were taken in order to derive this. So first of all, the first assumption is, as you know, that the mean values of these distributions, that is the mu y values, that will lie on a straight line. That is a basic assumption because we are studying linear regression. So that is an assumption. There can be also possibility that these mu values do not lie on a straight line. They can lie on a polynomial or whatever it is, quadratic. And this is the first assumption. The second assumption is the variance of this distribution. So the variance of these distributions are equal. So note that the distributions are not equal because the mean of the distribution, that is mu y values, that is dependent on these x values. So mu y values are changing. That is why the distributions are also different. This distribution I am talking about. But the variance of these distributions are equal. The third assumption is that there is no correlation between the y values. So the different y values, sample y values of the dependent variables, they are uncorrelated or not associated with each other. And finally the fi values, that means the distributions, these ones, these distributions are the normal distribution. That means the mean is mu y, of course, these mu y are the mean, and there is a variance which you don't know, but these variances are equal for these distributions. So you can take any x value and draw this distribution like this. If you draw this distribution, then the mean is always mu y, which is not constant, which is dependent on your x value, but the variance is constant. The sigma value is constant for all these distribution. So these are the assumptions for linear regression, simple linear regression. In the next video, we will see how to implement for a sample data using software like SPSS or Excel, and then we will try to interpret the result in a best possible manner. So until then, goodbye and thanks for watching this video.